Standard integrals of irrational functions, radical. Okay, so let's move on to a new type of integral. In the sections we've covered so far, we've been working with rational functions, that is, functions that can be expressed as a ratio of two polynomials. Specifically, we've looked at cases where the denominator, the bottom part of the fraction, was a quadratic polynomial, something like a polynomial with a highest power of 2. Now, this subsection shifts our focus to irrational functions. These are functions that involve roots, and we'll be concentrating on those where the denominator contains a square root of a quadratic expression. Think of something like 1 over the square root of x squared plus 4, for example. These types of integrals are often called radical integrals because of the presence of these radicals or square roots. Now, why are we learning these? Well, these integrals pop up a lot in real-world applications, particularly in fields like physics and engineering. For instance, when calculating the arc length of a curve, that's the length of a curved line, or when analyzing gravitational fields, you'll frequently encounter these integrals. Because they appear so often, it's incredibly useful to have a set of standard formulas to solve them quickly and efficiently, rather than having to derive them from scratch every time. And that brings us to the key technique we'll be using, trigonometric substitution. This is a clever method where we substitute trigonometric functions for parts of the integrand, the expression inside the integral, in order to eliminate the square root. We do this by leveraging trigonometric identities, those fundamental relationships between trigonometric functions like sine, cosine, and tangent. We'll see exactly how this works in the following slides, where we'll derive these standard formulas step by step. So, get ready to brush up on your trigonometry. Integration of \int frac dx sqrt x2, a $2. This integral form, integral of 1 over the square root of x squared minus a squared, arises when you have a difference under the radical, and the term with x comes first. Now, the formula for this integral is quite neat. It's the natural logarithm of the absolute value of x plus the square and the square root of x squared minus a squared, plus our constant of integration, c. Let's break down how we arrive at this formula. We'll use a technique called trigonometric substitution. Step 1, substitution. To get rid of that square root, we're going to use a trigonometric identity. Secant squared of theta minus 1 equals tangent squared of theta. This suggests we let x equal a times secant of theta. Step 2, differentiate. Now, we need to find dx in terms of theta. If x equals a secant of theta, then taking the derivative with respect to theta gives us dx equals a times secant of theta times tangent of theta, d theta. Step 3, substitute into the integral. Let's replace x and dx in our original integral with our expressions in terms of theta. This gives us the integral of a secant theta tangent theta d theta divided by the square root of a squared secant squared theta minus a squared. Step 4, simplify the denominator. Let's focus on simplifying the square root in the denominator. We can factor out in a squared, leaving us with the square root of secant squared theta minus 1. And as we mentioned earlier, secant squared theta minus 1 is just tangent squared theta. So, the square root of a squared times tangent squared theta simplifies to a times the absolute value of tangent theta. Step 5, simplify the integral. Now we can simplify the entire integral. The in the numerator and denominator cancel out, and the tangent theta terms also cancel, leaving us with the integral of secant theta d theta. Step 6, integrate. The integral of secant theta is a standard result. It's the natural logarithm of the absolute value of secant theta plus tangent theta plus our constant of integration, c. Step 7, convert back to x now. We need to express our answer in terms of x again. Remember, we initially substituted x equals a secant theta. So, secant theta equals x over a next, we need to find tangent theta. We know that tangent theta is the square root of secant squared theta minus 1. Substituting x over for secant theta, we get tangent theta equals the square root of x over a squared minus 1. which simplifies to the square root of x squared minus a squared, all over a. Now, let's substitute these expressions back into our logarithmic result. We get the natural logarithm of the absolute value of x over a, plus square root of x squared minus a squared over a, plus c. This can be rewritten as the natural logarithm of the absolute value of x plus the square root of x squared minus a squared, all over a, plus c. Remember from our log rules that the logarithm of a quotient is the difference of the logarithms. So the logarithm of x plus the square root of x squared minus a squared over a is the same as the logarithm of x plus the square root of x squared minus a squared, minus the logarithm of a, but since the logarithm of a constant is just a constant, it gets absorbed into our constant of integration, c. Therefore, our final result for the integral of 1 over the square root of x squared minus a squared is the natural logarithm of the absolute value of x plus the square root of x squared minus a squared, plus c. Okay, so let's move on to our first standard integral. As we discussed on the previous slide, we're now tackling integrals involving irrational functions, specifically those with square roots of quadratic expressions. This slide focuses on the integral of 1 over the square root of x squared minus a squared. This is a key formula to remember, and we'll see how it applies in various physics and engineering problems, as we'll discuss on the following slides. Integration of \int frac dx sqrt 2 x $2. This slide focuses on the integral of 1 over the square root of a squared constant minus x squared. Now, remember from the previous examples, the arrangement of terms under the radical is important. This form, integral of 1 over the square root of a squared minus x squared, arises when the constant term appears first in the difference under the radical. Let's look at the formula. The integral of 1 over the square root of a squared minus x squared is equal to the inverse sign of x over a plus the constant of integration. See, we write inverse sign as arcsin, so it's arcsin of x over a plus c. Now, let's go through the step-by-step derivation to understand why this formula works. Step 1 is substitution. To eliminate the square root, we'll use the trigonometric identity, 1 minus sine squared theta equals cosine squared theta. This is a key Pythagorean identity you should be familiar with. To make use of this identity, we let x equal a sine theta. Step 2 involves differentiation. If x equals a sine theta, then differentiating both sides with respect to theta gives us dx equals a cosine theta d theta. Now, step 3, we substitute these expressions for x and dx back into our original integral. This gives us the integral of a cosine theta d theta divided by the square root of a squared minus a squared sine squared theta. Step 4 is simplification. Let's focus on the denominator first. We can factor out a squared from under the square root, giving us the square root of a squared times 1 minus sine squared theta. And as we mentioned earlier, 1 minus sine squared theta is equal to cosine squared theta. So, we have the square to the square root of a squared cosine squared theta, which simplifies to a cosine theta. This simplifies our integral in step 5 to the integral of a cosine theta d theta divided by a cosine theta. The cosine theta terms cancel out, leaving us with simply the integral of 1 with respect to d theta. Step 6 is the integration itself. The integral of 1 with respect to theta is just theta, plus our constant of integration, c. Finally, step 7 is converting back to x. Remember, we made the substitution x equals a sine theta. Therefore, sine theta equals x over a, and if sine theta equals x over a, then theta equals the inverse sine of x over a, or arcsin of x over a. So, putting it all together, we arrive at our final result. The integral of 1 over the square root of a squared minus x squared is equal to the inverse sine of x over a, plus the constant of integration, c. This formula is crucial, and we'll see it pop up again in various applications, as we discussed on the introductory slide, particularly in physics and engineering problems. Keep this one memorized alongside the others we've covered. On the next slide, we'll tackle another standard integral, so let's move on. Okay, let's move on to our next standard integral. As we discussed in the previous slides, we're dealing with integrals of irrational functions, specifically those involving square roots. Integration of \int frac dx sqrt x2, a $2. Okay, let's move on to our third standard integral. As we saw in the previous slides, we're dealing with integrals involving square roots, these radical integrals. Now, this slide focuses on this integral of 1 over square root of x squared plus a squared dx, arises when we have a sum of squares under the radical sign. Remember, in the previous slide, we had a difference of squares, and before that, a difference under the radical with the constant term first. This one is different. We have x squared plus a squared inside the square root. The formula for this integral is integral of 1 over square root of x squared plus a squared dx equals log absolute value of x plus square root of x squared plus a squared, plus the constant of integration c. Let's break down the derivation step by step. First, we need to make a substitution. We're going to use the trigonometric identity 1 plus tangent squared theta equals secant squared theta. This identity is key because it allows us to eliminate the square root. So, we let x equal a times tangent of theta. Next, we differentiate both sides of this substitution with respect to theta. This gives us dx equals a times secant squared theta d theta. Now, we substitute both x and dx into our original integral. This gives us the integral of a secant squared theta d theta divided by the square root of a squared times tangent squared theta plus a squared. Let's simplify the denominator. We can factor out a squared from inside the square root, giving us square root of a squared times tangent squared theta plus 1. And, using our trigonometric identity, we know that tangent squared theta plus 1 is equal to secant squared theta. So, the denominator becomes square root of a squared times secant squared theta, which simplifies to a secant theta. This simplifies our integral to the integral of a secant squared theta over a secant theta d theta. The terms cancel out, leaving us with the integral of secant theta d theta. Now, you should recall from your calculus that the integral of secant theta is log absolute value of secant theta plus tangent theta, plus our constant of integration c. Now comes the crucial part. Converting back to our original variable, x from our initial substitution, we know that tangent theta equals x over a. We also need to express secant theta in terms of x. Remember the identity secant squared theta equals 1 plus tangent squared theta. Taking the square root of both sides, we get secant theta equals square root of 1 plus tangent squared theta. Substituting x over for tangent theta, we get secant theta equals square root of 1 plus x over a all squared, which simplifies to square root of 1 plus x squared over a squared, or square root of a squared plus x squared, all over a. Now, we substitute these expressions for secant theta and tangent theta back into our integrated form. This gives us log absolute value of square root of a squared plus x squared over a plus x over a plus c. Notice that we can simplify this further. The log of a fraction is the log of the numerator minus the log of the denominator. Since log of a is just a constant, it gets absorbed into our constant of integration, c. This leaves us with our final result. Log absolute value of x plus square root of x squared plus a squared plus c. So, to recap, this integral is frequently used in physics, particularly in kinematics, as we'll see on the next slide. Remember the substitution, the trigonometric identity, and the careful back substitution to arrive at the final result. And as always, don't forget that constant of integration, c. Real-world application example, physics kinematics. This slide highlights applications in physics, specifically within the field of kinematics, which deals with the motion of objects. These integrals frequently appear when analyzing scenarios involving forces and movement. The slide states that these integrals are used to determine the velocity of an object experiencing gravity and air resistance, or to calculate the time it takes for a particle to travel along a specific path. Think about it. Air resistance often introduces square roots into the equations describing motion, and these integrals provide the tools to solve those equations. Let's look at a specific example. Suppose we have a particle, and its velocity, which we'll denote as v, is given by the equation v equals the square root of x squared plus a squared. Now, if we want to find the time, t, it takes for this particle to move from an initial position, x1, to a final position, x2, we need to integrate the velocity with respect to distance. That means we need to evaluate the definite integral of 1 over the square root of x squared plus a squared, with the limits of integration being x1 and x2. Notice that this integral is exactly the third formula we derived on the previous slide. We found that the integral of 1 over the square root of x squared plus a squared is the natural logarithm of the absolute value of x plus the square root of x squared plus a squared, plus a constant. So, by applying that formula and evaluating it at the upper and lower limits of integration, x2 and x1 respectively, we can directly calculate the time taken for the particle to travel that distance. This demonstrates how these seemingly abstract integral formulas become powerful tools for solving concrete problems in physics. Okay, let's move on to slide 5. As we've been working through these standard integrals of irrational functions, it's important to understand why we learn these techniques. It's not just about memorizing formulas, but about applying them to real-world problems. This is a good bridge to the next slide, where we'll summarize the key takeaways and also discuss some common mistakes students make when working with these integrals. Key takeaways. Okay, let's recap everything we've learned about integrating irrational functions. This slide, slide 6, is a really useful summary, almost like a mini cheat sheet, to help you quickly recall the key formulas we've derived. As you can see, it's presented as a table neatly organizing the integral form, the trigonometric substitution we use to solve it, and the final result. Let's go through each row. The first row shows the integral of 1 over the square root of x squared minus a squared. We said earlier that this form appears when you have a difference under the radical. To solve this, we use the substitution x equals a secant of theta, that sx equals a sec theta. And after carefully working through the trigonometric substitution and simplification, we arrived at the result. The natural logarithm of the absolute value of x plus the square root of x squared minus a squared, plus our constant of integration, c. Now, moving down to the second row, we have the integral of 1 over the square root of a squared minus x squared. This is the case where the constant term comes first under the radical. Remember, we used the substitution x equals a sine of theta, x equals a sin theta, for this one. This led us to a much simpler result, the inverse sine of x over a, plus our constant c. This is also written as arcsin of x over a. Finally, the third row presents the integral of 1 over the square root of x squared plus a squared. This occurs when we have a sum of squares under the radical. For this, we employed the substitution x equals a tangent of theta, x equals a tan theta. And, interestingly, this also resulted in a logarithmic function, the natural logarithm of the absolute value of x plus the square root of x squared plus a squared, plus c. Notice that 2 out of the 3 results involve a natural logarithm, while the other involves an inverse sine function. It's crucial to remember which substitution leads to which result. This table is designed to help you do just that. Keep this slide handy as you practice more problems. And remember, we'll be building on these concepts in future sections, so a solid understanding of these standard integrals is essential. Also, don't forget to review slide 7, where we discuss common mistakes to avoid when working with these integrals. Common mistakes to avoid. Okay, let's move on to the final slide, which highlights some common mistakes students make when tackling these radical integrals. It's good to be aware of these before you get stuck, so let's go through them one by one. 1. Confusing the logarithmic forms. A very frequent error is mixing up the final results for the integrals involving the square root of x squared minus a squared and x squared plus a squared. Remember, both of these integrals do lead to a natural logarithm, a log function, in the final answer. However, pay very close attention to the sign inside the square root in the original integral. The sign inside the square root in your final logarithmic answer must match the sign in the original integral. So, If you started with the square root of x squared minus a squared, your final answer's square root term must also be x squared minus a squared. Don't swap them. 2. Incorrect substitution. Another common mistake is choosing the wrong trigonometric substitution. For example, attempting to use the substitution x equals a sine theta for an integral with the square root of x squared plus a squared is incorrect. The key here is to match your substitution to the trigonometric identity that will simplify the expression under the radical. Remember, we used x equals a secant theta for x squared minus a squared because of the identity secant squared theta minus 1 equals tangent squared theta. And we used x equals a tangent theta for x squared plus a squared because of the identity 1 plus tangent squared theta equals secant squared theta. Always think about which identity will eliminate the square root. 3. Forgetting the absolute value. This is a small but important detail. When you have a logarithmic result, that is, a natural log in your final answer, always include the absolute value sign around the argument of the logarithm. That's the expression inside the log. The reason is that the logarithm function is only defined for positive arguments. So, writing log absolute value of expression ensures that your answer is mathematically valid for all possible values of x. 4. Ignoring the constant $. Finally, and this is a mistake made in all indefinite integrals, don't forget to add the constant of integration, c, at the end of your answer. Remember, indefinite integration represents a family of functions that differ only by a constant. So, including plus c signifies that your answer is the most general antiderivative. So, keep these common pitfalls in mind as you practice, and you'll be well on your way to mastering these standard integrals of irrational functions. Now, that concludes our discussion on this topic. Are there any questions before we move on?